complete the solution in which we are to design a rock foundation. The problem rises as it is found that an upper plate are underlain at about 10 meters of soft to medium grade on the construction site. In this video, we will be covering the shear force diagram, bending moment diagram, the required thickness of the rod foundation, the number and the required steps for reinforcement bars.
Hello there. So I will be starting the problem with calculating the sole pressure of the rough foundation. So let's go.
So first of all, we refer to the plan and obtain the base and the length, and then we calculate for area as well as the moment of inertia for x and y. Then we multiply the load column by 1.5, which is the load factor. Then we sum up all the total factored loads into one, which is labeled as Q, and then we find out Q1x, Q2x and Q3x. How do we find that? Is by, for example, Q1x is at column 2 for A2, B2, C2 and D2. As well goes for Q2x and Q3x. Just the numbering may be confusing to you, but you'll understand later. Next, we find out x1, x2 and x3. How we find that is x1 is from A1 to B1. A1 to A2. Whereas for x2 is A1 to A3, and x3 is a little bit smaller. It's because A1 is not exactly on the column, it's on the side, so we have to add 0.125 to get the center of the column, which is x3. Then we obtain x prime. X prime is by adding up the sum, adding up all the multiplication of Q1x to x1 as well as Q2x to x2 and Q3x to x3, and then divided by the total load that we calculated just now. And then we obtain EX, which is x prime minus b over 2, where b is the base. Therefore, we obtain my, which is Q of the total load times EX that we just calculated. So from there we would obtain whether it's positive and negative, and due to the positive side, it is to the right center of the map. Okay, so next, the next procedure is the same. Because it just changes from, instead of column 2, we Q1y is from A1 until A3 instead of A1, B1, C1. No, this is different, but in the terms of calculation it is similar, where yx is equivalent to L over 2, where it uses length instead of base. So then we obtain EY. So y prime minus yz, and equivalent to 0.089, and then we multiply it with the total load to obtain mx, which is negative, so it is located to the right center of the map due to y-axis. And then from there we could calculate the sole pressure for each column by getting the total load divided by the total area plus my times with x1 for A1, for example, divided by moment of inertia for Iy plus mx for A1, yx for A1 over 1x. This is particular because this is at column A1. For certain reasons, for example at A3, Q over A minus my x 1 over 1y because of the location of the column at the plan. So that's why we induce how we produce whether it's plus plus minus, minus plus, and eventually minus minus, for example at QD3. So my part ends there, but it will be continued by Muhammad Faid. Thank you.
Hey, Assalamualaikum warahmatullahi wabarakatuh, and a very good evening for everybody. So my name is Muhammad Faid Wajuddin bin Rizwan. So I'm going to resume from my colleague, which is Muhammad Izzuddin bin Burhan. So today I'm going to show you how do we calculate over the shear force and bending moment diagram for this particular problem. So if you really see on this diagram, how do we come up with this diagram is that the first thing that very important for us to know is that we have to know what is the point load and how much is the uniform distributed load. How come you have a uniform distributed load? Because this actually is the soil pressure that exerts on the foundations. So if we can see how do we get P1, P2, P3 and P4, that's because first we are using this load factor, which is this load factor, and then we multiply with the given data, with the A1, B1, C1, D1, with the load given data, which is already multiplied by the load factor 1.5. So when we are calculating for the uniform distributed load, which is the soil pressure, we can see that the uniform distributed load is going to be P, which is the base, times with the QAVM1. What is the QAVM1? It is the average soil pressure. Okay, so that is how we come up with this diagram. When we get into this diagram, it's going to help us a lot. How can we come up for the shear force diagram and the bending moment diagram? So let's see on the shear force diagram first. Okay, so for the shear force diagram at first, okay, as we can see, it's going to be like 30.42 kilonewton. Okay, so how do you come up with 30.42 kilonewton? First is we're going to use the uniform distributed load, which is 243.359, multiple with the length of the end at the starting point until the distance at P1. So it's going to be 0.125. So 0.125 multiple with 243.359, we're going to get 30.42 kilonewtons. And then we minus with the P1 value, which is 625.8, we will get 595.38 kilonewton downward, because it was downward, so it's going to be the opposite of the uniform distributed load. And then we plus with the 243.359 multiple with the distance from P1 until P2, then we will get 4x0.44, and then we minus with the point load number 2, which is 1564.5, and then we will get 724.09 until it comes for the rest, until it reach 0 kilonewton. So that's important for shear force diagram. It must close to 0. That shows it is balanced. And then we come up for the how do we come up for the bending moment diagram? It's simple. It is the area under the graph for the shear force diagram. So if we calculate the area of the triangle, which is 1/2, multiple with 30.42 and multiple with distance, we will get the area. The same concept go like the shear force diagram, which is with minus, and then when we get the area, and then we minus with the area this particular area below the neutral axis line, then we get the value for the maximum. And then at the same process, we repeat until for the last, and then we will get this bending moment diagram. So that's all from me. Thank you very much.
My name is Muhammad Izzuddin bin Rizwan, and I will be explaining for the part B for the assignment model, for the given assignment.
The part B will be calculating the reinforcement requirement in y direction. Here have given the FC and Fy, the value of FC, Fy with the load factor of 1.5. For the first step, we're going to assume the U. We're using the U is equivalent to 1200 times with 1.5 kilonewton, which is this is the factor where we take the value of U, which is the highest value of for the H strip for the third
column, which is the 1200. So this is our U value. After we got the U value, where the beta alpha lambda has already been given, and then we put inside this formula VC, where you have three formula of VC, where the difference is the first VC is 1/6, the second is 1/12, and the third one is 1/3. And then we substitute all the value, and we get the D is equivalent for the first one is 0.7689, etc, etc. And then after we have get that, we choose the highest number of D to where we can find the thickness of the slab, where H is the thickness of the slab. Okay, where H is the thickness of the slab, where we take the highest value of the D and we plus it with the 76. This is the minimum cover, where we assume is 76 millimeter, and this is the radius of the posterior bar, where the diameter of the bar we assume is equivalent to 35 millimeter. And then we move on to the next part, where this is the maximum moment for the positive moment, this is maximum moment for the negative moment, where we get from the second bar from the previous example. This is one where the maximum positive moment is 169 and the maximum negative moment 176, and then we divide it with B, which is 6, where we get this value. And after that, we're using this formula for the A formula to find, after we arrange the formula, we get the AY is equivalent to 0.03519A. So for the next part, we want to find the area of AY, where we can find the variable of A using this formula. This is 194, where we get from the previous answer, which is the maximum moment. You should put it inside here, and then we arrange the equation, and then we get the L value is 0.02489 and 1.195, where we choose the smaller value, and then we substitute back into this equation, and we get our area of steel, which is equal to 874.47. And then where we refer the AS provided with the Euro code from the RC design, from the RC design, and then we get the diameter of the bar is 60 millimeter, equal with 235 millimeter center to center. And then we repeat this step, same for the negative reinforcement, and until the finish one. But for the next part, where we see, okay, but this is an extra calculation, because the negative moment occur at mid bay, where there's a negative moment occur at the mid bay of this bottom steel bar. Therefore extra reinforcement should be provided. And then we're using the same step as above, but the moment here we take is this moment, where it located at the bottom of the steel. Then we repeat the step again, thus we get the value of E for each step. AY is 0.876, and then we're using this first step where we refer with the Euro code, and we're using 60 millimeter diameter with 235 millimeter center to center. And then we get everything, we get all the steel bar requirement here, 20 millimeter and 20 millimeter. That's all from us. Thank you.